The binary number system works the same way as the decimal number system. The only difference is what each of these places represents. This is a 4-digit binary number, 1010. Each of these digits can also be called a bit, since a bit represents 0 or 1. Now this 4-digit number equals the decimal number 10, and we're going to see why. This first place, this is the ones place, just like in decimal. Now there's a 0 here, so that means we're going to multiply 0 times 1, get the very exciting value of 0. The second place, the second bit here, that's where things get more interesting. This is actually the 2's place, not the 10's place. And there's a 1 here, so we're going to multiply 1 times 2. So far, this number equals 2. The third place, the third bit, this is 0, and this is the 4's place. So we're going to multiply 0 times 4, which is once again just 0. And we're still looking at the number 2. Finally, this fourth bit here, this is the 8's place, and there's a 1 here. So we're going to multiply 1 times 8. Add that to everything else, we end up having 8 plus 2, which equals decimal 10. In the decimal system, each of these places represented a power of 10, but in the binary system, each place represents a power of 2. The first bit is 2 to the 0 power, it's 1. The second bit is 2 to the power of 1, the first power, which is 2. The third bit is 2 squared, 2 to the power of 2, which is 4. And this fourth bit is 2 cubed, 2 to the power of 3. That's 8. That's the only difference between decimal and binary, what each place represents. Once we know that, we see what digit is in each place, we multiply them together, and we get our final value. Now let's try to convert another binary number to decimal. I'm going to erase this work here, and then for the number, let's just flip the bits. 0 becomes 1, 1 becomes 0, 0 becomes 1, and 1 becomes 0. What do you think this equals in decimal? I'll give you a second to think about it. All right, now let's figure it out together. There's a 1 in the ones place. So this so far equals 1 times 1. That's 1. There's a 0 in the 2's place. So we add 0 times 2. That's 0. There's a 1 in the 4's place. So we add 1 times 4. That's 4. So far we've got 4 plus 1. And then there's a 0 in the final place, the 8's place. So that's 0 times 8, or 0. So we've got 0 plus 4 plus 0 plus 1, which equals 5 in decimal. Let's try converting a bigger binary number to decimal. We know that this equals 5. What happens if we add 4 more digits to the left of these 4 digits? Let's start by figuring out what each place represents. One way of doing that is just to double the previous places. So this place here is 16, this place is 32, this place is 64, and this place is 128. Another way of doing this is to calculate the powers of 2. So this place is 2 to the 4th, which is 16. This is 2 to the 5th, which is 32. This is 2 to the 6th, 64. And this is 2 to the 7th, 128. Okay, so now we know what each place represents. Now we can add these numbers up. We know already that these ones equal 5. We already did that. Now let's add in what we've added here. So we have a 1 in the 16. So that means we're going to add 16 to the number. Then there's a 0 in the 32. So that's just going to be 0. There's a 1 in the 64. so that's going to be 64. And there's a 0 in the 128, so that'll be 0. So now we've got 64 plus 16 plus 5. So that's 80 plus 5, which is 85 in decimal. So it took us 8 bits to represent a number that only takes 2 digits to represent in the decimal system. That's because each bit represents less information, just 0 or 1 instead of 0 to 9. But it's easier for computer hardware to store binary values, so binary numbers and the binary number system are the foundation of all computing.